It's really a pleasure to introduce Taesoo Kim today. He is a graduating PhD student at MIT and the group that advised by Nikolai Zeldovich and Franz Kaschek. And what he's going to be talking about is, I think, something that's near and dear to all of us, which is, okay, you just visited some web page or downloaded some app, and your disk starts spinning and you don't know why. And you'd really like to have undone what you just did. So he's going to explain how to recover from some giant mistake you didn't realize you were about to go make that you did make. Okay.
Thank you for the introduction. I'm Taesoo Kim from MIT. Today, I'm going to tell you about automatic intrusion recovery with system-wide history. As a researcher working on system security, we've been trying hard on preventing attack. We developed lots of tools and techniques to harden our computer system. I also have been working on a lot of proactive security mechanisms that help us prevent attack. I designed security mitigation technique in cloud and mobile. I also built a practical sandboxing system and a new security mechanism in Linux as well. However, despite of these efforts to prevent attack, we realized that attackers routinely compromise our computer system. For example, a few months ago, a group of hackers penetrated into Google's infrastructure and changed the landing page. Similarly, Facebook has been remotely exploitable for more than a year. Even worse than that, millions of projects in GitHub have been vulnerable ever since the GitHub was created. Of course, our desktop computer were not the exception. Unfortunately, the compromise of our computer system are in fact inevitable, because a single innocuous bug can easily lead to system-wide compromise. And as a programmer, it's really hard to write bug-free software. Even if you write the bug-free software, administrator might misconfigure their policies and permission in their software, and user might choose weak and guessable password. What I want to argue today here is that we need both proactive security mechanism trying to prevent the attack at the first place, and at the same time, we need reactive recovery mechanism that we might be able to invoke once those inevitable compromises happen. Also, recovering integrity after those compromises is really important. In fact, it is required to continue operating our computer system. But what we have today for recovery is very limited. For example, antivirus tools is only good at repairing from predictable attack based on the signature that we analyze ahead of time. With backup tool, as far as we schedule it regularly, we might be able to recover the whole salvage of attack with an earlier backup. But what if attack was detected days or weeks later? Then recovering with an earlier backup might discard all the changes that we are making after the attack. Since neither of those tools are quite satisfactory, what administrator ends up doing is spending days or weeks of manual recovery in order to track down all the effects of the attack. Now, even after spending this time, there is no single guarantee that we completely remove the attack from our computer system. Let me show you a real attack instance and its recovery that happened in kernel.org. The kernel.org is the main repository of code for the Linux kernel. It was a lot of open source projects, including Git and Android at the time. And this is a timeline of kernel.org attack. On August 28th, the administrator detected that the kernel.org had been compromised by an attacker because they noticed some weird error messages from a program that they never installed themselves. After they found out these error messages, they started investigating the attack. After 3 days of investigation, they found out that the initial break-in likely happened about a month ago because the Trojan security shell server was modified around the time. You know what they end up doing after this investigation? They decide to fully reinstall all of the suspicious server with the latest backup. In fact, at this point of time, the recovering with an earlier backup is only safe option, because after secure shell was modified, there are too many suspects to clean up manually. Unfortunately, recovering itself is not that easy. Even by security experts, it took about a month to fully recover from this attack. Of course, during that time, site went down and unavailable for public use. Let's just think about then what are the problems in today's repair strategy? We often see this pattern in the real world. First of all, because we manually analyze the attack, the recovery process becomes tedious and time-consuming. In kernel.org attack, it took about a month to fully recover from this attack, even by security experts. Secondly, even we since we often recover with an earlier backup, after recovery, we end up losing a lot of changes that we are making after the attack. In kernel.org, we end up losing developer's public key and all the bug report that was updated during that period. And lastly, even after recovering with an earlier backup, after recovery, there is no single guarantee that we completely remove the attack from our computer system because the attack could have happened much earlier than our backup. Then how can we solve all of those problems? In other words, how can we design automatic recovery system that preserve the legitimate changes and at the same time provide very strong guarantee about our recovery? And this is the key question that I like to answer during the talk. The core idea that I'm proposing here is to keep complete history of computation. In fact, our computer system is just getting input and generating output at a particular time, but this is not enough to understand what was happening in our computer system. So let's represent our computer system in much fine-grained detail. By representing our history in this way, we now have great opportunity to track down the attack. Not only we can track down the attack, but also we can go back and change our history. If we can change our history, the recovery problem is nothing but to cancel the initial attack input. After we cancel the initial attack input, we can reconstruct our system history by using history of computation. Then we can make our computer system as if the attack never introduced at the first place. One nice thing about this approach is that we turn the problem of manual recovery into problem of manipulating history. In fact, there are a lot of challenges in implementing this idea as a real system. First of all, existing systems are not specifically designed for history in mind. I mean, there are tons of implicit dependency probably in your application and underlying kernel, and also there are tons of implicit use of the timeline. In current operating system, we don't exactly know how two files are related and how they are created. Secondly, even if we have this complete history, detecting attack is not an easy task because attack can be anywhere in our history, and also attacks are often detected days or weeks later. Lastly, in some cases, history cannot be changed at all. What if we send out the spam in our history? And for example, what if we fire a missile from our computer system? There is no general way to revert those operations in our history. However, in fact, we developed lots of different techniques attempting to overcome those challenges and implement as a real system, including automatic recovery system in operating system, and web application, and recently distributed web services. Not only that, we also developed an automatic way of detecting past attack in web application. Today, I'm going to talk about my original idea of automatic recovery in operating system and automatic way of detecting past attack by using security patch. And lastly, I'm going to talk about my future research agenda. So let's first talk about retro. In order to understand how retro works, let's consider an example attack scenario. In our attack, there are 3 parties involved, including attacker, an administrator, and Alice. Attacker at the top first penetrate into our computer system and add a new account for himself by modifying the password file. And then attacker installs some Trojan PDF LaTeX binary because he's smart enough to know that our paper deadline is coming. We might invoke the PDF LaTeX binary later. So after this intrusion, administrator comes along and adds a new account for Alice by modifying the password file. And then Alice logs into my computer system by using secure shell. At that moment, secure shell server has to read the modified password file that was modified by attacker and administrator. And then Alice runs the Trojan PDF LaTeX binary to typeset her paper for submission. Then how can you recover from this attack? Well, we are talking about how to recover from this attack by using history. The one popular way to keep track of the history is to use the idea of taint tracking. In our taint tracking, we're going to keep track of systems objects, including process and files, which I mark as green color here. At runtime, we're going to keep track of their dependency between process and files. For example, if attacker process write down to the password file, we're going to create a dependency from attacker process to the password file. Then we now have this execution history by using taint tracking. Then how can we recover from this attack? Well, once you identify the attack in our history, by using taint tracking, we can track down all of the affected files and process, and we can just restore those files from an earlier backup. For example, once we identify the attacker process in our history that I mark as a red color here, by using tail tracking, we can track down all of the affected files and process in our history, and we can just restore those affected files with an earlier backup, namely PDF binary and password file. After recovery, we could remove the Trojan from the PDF LaTeX binary, and also we can remove the attacker's account from the password file. However, this scheme has a single problem, namely false positive. It means that after recovery, we end up losing Alice's account and files that are not actually affected by the attacker. Then how can you preserve Alice's account and file after this recovery? One possible way to preserve those changes is by re-executing all the legitimate operation made by admin and Alice after recovery, after intrusion. So one well-known way to enable such re-execution is to use the idea of VM rollback and replay. So we're now going to consider our entire system as a single virtual machine. In our virtual machine, we have input and output, and also we periodically checkpoint the state of the virtual machine that I mark as a green color here. Then we are pretty much ready to recover from this attack. Once we identify the attack in our history, we're first going to roll back our entire system even before the checkpoint. And then we're going to re-execute all the past input except the attack. Someone might imagine at the high level, this scheme might give us correct state where we could remove the attack from our computer system, and at the same time, we can preserve all the legitimate changes made after that. However, this scheme is suffering from two significant problems. First of all, VM rollback and replay is quite expensive. It means repairing a weak old attack requires another week solely for replay. More subtle problem is that the past input to our virtual machine are now meaningless to our new system because there are tons of non-determinism while replay, and we might create new secure shell crypto key while re-execution. And probably all the application might have different state. More subtle problem here is that the traditional deterministic replay technique will not work in our case because we actually expect the change of the state after recovery. And how can we solve those problems? The retro's way to solve this problem is to define our new abstraction we call data action history graph. In retro's action history graph, we represent fine-grained history. It is so fine-grained that it includes a lot of kind of objects and system calls and their argument, and even some of the function code. Also in retro, we assume we are using tamper-proof kernel and storage so that we can keep our action history graph secure. For actual recovery, we're first going to roll back the objects that are directly affected by the attack. By doing so, we can avoid the false positive of tail tracking that ends up recovering all the files in their system. After rolling back those objects, we're going to selectively re-execute some of the actions that are indirectly affected by those changes in our history. By doing so, we can avoid the expensive VM rollback and replay. Let me explain how we can actually recover from this example scenario by using retro. In retro's action history graph, we have objects that represent files and processes in our operating system. In our slide, we have 4 such objects, including attacker process, password file, and user Alice, and admin shell. And in our action history graph, each object has a set of actions that represent their execution. For example, all the system calls in our operating system are considered action in our action history graph. Also, each action has a set of dependencies. For example, if attacker process write down to the password file, we're going to create a dependency from attacker process to the password file. Similarly, if admin shell invoke the @user process, we're going to create dependency from admin shell to @user process. And then @user process read and write down to the password file and return back to admin shell. We also have a notion of checkpoint to preserve the state of the object that I presented as a green circle here. And then we are pretty much ready to recover from the attack. After you identify the attack input, namely write operation of attacker process, we're first going to roll back the objects that are directly affected by the attacker. Here we just roll back the password file because the password file was modified by attacker process. After rolling back this password file, we're going to remove the attacker's operation in our history. And then we're going to re-execute some of the operation, some of the action that are indirectly affected by those change in our history. Here we just re-execute the read system call of a user process because the read system call was affected by the parser file. Because this read system call affect the execution of a user process, we first gonna roll back the user process and re-execute, starting from exec system call. This point illustrates our key advantage over VM replay. Unlike VM replay that ends up rolling back entire system and start executing, here we just roll back the parser file and re-execute a single process in order to recover from this attack. And then we're gonna keep re-executing the user process. And here we just write down the LSS account to the parser file. And this point illustrates our key advantage over taint tracking. Unlike taint tracking that ends up losing the LSS account after recovery. Here, not only we can remove the attacker's account from the parser file, we preserve the LSS account by re-executing a user process. This scheme works great, except that I skip over one important detail here. According to the rule that I was describing so far, after re-executing exit system call, we have to roll back the entire admin shell because exit status affect the execution of admin shell and secure shell server all the way up to the login session. It means that this naive process level re-execution require re-execution of all processes in their system. Then how can we solve this problem? The key observation that we made is that admin shell was not actually affected by the attacker because the invocation of adduser Alice succeeded as before, and this is what administrator wanted to do at the first place. If the invocation failed, we have to re-execute entire execution of admin shell, which is the correct thing to do. If the invocation succeeded as we expected, we can just stop propagating re-execution to the admin shell. And for example, instead of rolling back the admin shell, we can now apply our idea, the predicate, to the exit system call so that we can check if this exit system call succeeded as we expected. But if that is the case, we can stop re-execution of the admin shell. Let me consider another example. Similar to the previous one, attacker process write down to the parser file, and then Alice's secure shell server read the modified parser file. In order to recover from this attack, we first have to roll back the parser file, and also we have to roll back the Alice's secure shell server. It means that we have to roll back all the processes that are inherited from Alice's secure shell server. How can we solve this problem? The key observation that we made is that Alice's secure shell server was not actually affected by the attacker because Alice's secure shell server checked only Alice's accounts, not the attacker's account. And this is what Alice's secure shell server wanted to do. If the Alice's account changed while re-execution, we have to re-execute entire secure shell server. If the Alice's account doesn't change, we can stop propagating this re-execution to the Alice's secure shell server. And this is the machinery that enables this observation we call refinement. With refinement, we can embed high-level semantic in our action history graph. Here, we just represent capitable name function of Alice's secure shell server. Capitable name function is a function, get username, and return corresponding password entry. So by representing capitable name function in our action history graph, instead of rolling back the entire Alice's secure shell server, we can now just roll back a single function and start re-executing this corresponding function. And then in order to avoid the duplicate computation while re-execution, we're gonna apply our previous idea, the predicate, to check if this capitable name function returns the same Alice's password entry. If that is the case, we can skip the re-execution of Alice's secure shell server. And this is a quick summary of our approach. We first represent our history in fine-grained way with our new data abstraction we call action history graph. In order to make this approach more practical, we introduced two new techniques, predicate and refinement. With predicate, we could skip the equivalent computation while re-execution. With refinement, we could re-execute fine-grained action in our action history graph. However, there's one more challenge that I didn't talk about so far, is the external dependency. What happened if the attack was externally visible? What if we send out the spam or fire missile? It's really hard to solve in general, but instead of addressing this problem further, we simply ask user for decision about current situation. But fortunately, in some cases, we can actually help users to understand the current repair state. For example, we can notify user about the spam email that we just sent out, or we can notify some of the changes in our terminal output. Well, what's happening here is that we printed out the authorized key file. That is a file that allows us to log into our computer system without further authentication if there is a public key in it. When we printed out this authorized key file, we could see some attacker's public key in the middle. So after recovering from this attack, what we are notifying here is that, hey, you should not see this attacker's public key in the terminal because we repair our current system accordingly. We're going to see this one in our demo shortly. Let me quickly talk about our implementation. Retro consists of two components. Yes?
So just a little bit of clarification. So if the system administrator happened to log into the attacker's account, then presumably everything that they would get after that would be tainted.
Yeah.
And then you'd be dead, right?
Yes. That is another external dependency you have to resolve.
Okay. Well, not necessarily external, it would be internal.
You can think of this way: a password passed to you as a human, and you put something to the computer. We're actually missing this dependency from computer to the human. This is another way of thinking of the external dependency.
Yeah, in the case where the system administrator happened to super user into Alice, then your system would actually not propagate that.
That's true.
Okay.
Okay, our system. Oh, sure.
Another question. So I certainly understand that you can't reverse the spam that went out, but I'm also curious about issues where during re-execution you're in a state that requires user input.
Yes. Whenever you need whenever we need some user input to our system, we actually just pause and ask for further users' input about our system. It's naturally integrated to our recovery. Okay. Retro consists of two components: a runtime component and recovery. At runtime, we're gonna record action history graph by interposing every single system call of Linux. Whenever a process makes a system call, we're gonna resolve all the dependencies between kernel object and create action history graph. After we have this action history graph, we can start recovering from this attack. So for actual recovery, we implement a repair controller and set of repair manager. One nice thing about this separation is that if application developer want to implement application-specific undo and redo manager, they can simply use the API that repair controller provide, so that they can improve the performance of re-execution. So let me show you a demo. So we're gonna change my terminal. It's nice to see. We're first gonna run our demo. What I'm going to do is that I want to run a PDF viewer called Slider that I'm using for my presentation as well. I'm gonna open my paper called paper.pdf, of course. So I'm gonna run this slider.paper.pdf. What I'm going to do is that, hey, while reading this paper, let's say we found an interesting URL, the google.com. Would you like to click this URL? We often click this URL all the time. It's just naive google.com. But in fact, if you click this URL, everything can possibly happen in your system. So let me see what's going to happen in my computer system. And this is mouse. Probably you can see it. Yes. So when we click this URL, something weird happened. But in order to make this situation more interesting, so let's say we didn't see this weird stuff and continue using our operating system. So let's say we are done with this paper, so we're going to terminate this application. And what I'm going to do is that I want to install the public key to my computer system by simply appending my public key to the authorized key file here. I simply append my public key to the authorized key file. After install my public key, I want to see whether I could correctly install my public key by printing out the authorized key file. Of course, interestingly, we have new public key at the bottom, but interestingly, there's an attacker's public key in the middle. It means that attacker could have logged into a computer system and can do anything on behalf of your credential. Then how can you recover from this attack? Well, if you're using Retro, we provide a nice tool for interactively navigating your history. We call Backtracer. In Backtracer, we basically display the hierarchy of process in your history. What's interesting here is that this is my program slider. Can you see it? With the paper. When you click this link in slider, the slider tries to invoke the Firefox with the URL. But unlike Google.com, URL was crafted so that instead of running the Firefox with the Google.com, it actually skipped the invocation of the Firefox. We printed out some help messages and actually download a virus from attacker's computer, of course my computer, and change its permission and actually execute. It's a really terrible situation at this point because the virus could access anything on your computer system. But this is a real vulnerability that exists in the slider, the latest version of the slider. So in order to understand what was happening, let's include more file-level dependency in our graph. So of course, this virus accessed the authorized key file, or the rest of the tools that I use for installing my public key also access the authorized key file. Now, how can you recover from this attack? Well, I want to cancel my last click in my slide. It means that I want to cancel the invocation of the shell so that I can remove the virus from our computer system. At the same time, I can restore my authorized key file that virus modified it. So actually, in order to cancel this node, we provide this command. So before we actually execute this command, let's first check our state of our computer system. When I list off files, of course, there is a virus in my home directory. And also, in authorized key file, there is attacker public key in the middle. So in order to recover from attack, I'm gonna execute this repair command. It means that I want to cancel the invocation of the shell if the exec system call contains the virus string in it. If you cancel this single exec system call, you can actually recover from this entire virus. So let's execute this command. We first scan the entire system, and what we are notifying here is that, hey, you should not see this attacker's public key in the middle because we repair current system accordingly. So what's interesting here is that at the beginning of repair, we first remove the virus from our computer system and also restore the authorized key. What's interesting here is we also restore X authority key file we couldn't catch at the first place. It means that our system actually provides very precise dependency tracking in your system. So let's check our current state. Of course, we remove the virus. And in our authorized key file, we could remove the attacker's public key in the middle. What's interesting here is that we preserve the new public key that we install after the intrusion by using all the machinery that I was talking about today. So let's go back to my slide. And however, the problem in this approach is that in our demo, we already knew what's going to happen in our computer system when I click this URL. So detecting entry point of attack seems quite easy. But in fact, detecting entry point of attack is quite difficult. For example, how can I find an attack that took place about a month ago? There's too much information at the low level. So detecting entry point of attack for automatic recovery itself quite tedious and time consuming. Now, how can we solve this problem? The key observation that we made is that the security patch can render the attack harmless. For example, let's say we escape the URL argument for the Firefox. Instead of sending the crafted URL to the Firefox, let's say we correctly escape it. If we escape this URL argument, then the unpatched version of unlike the unpatched version of execution, then download and invoke the virus. In our patched version of execution, we actually block the invocation of virus. What does it mean is that by comparing the history of both execution, we can actually detect the past attack. Then how can we get the history of the patched execution? I mean, well, since we have all the history in our system, why not just replaying the past input after applying the security patches. Then if the patched execution generate different history, we can consider the original past input is potentially malicious to our computer system. Of course, one nice thing about this approach is that we turn the manual efforts of auditing process into computational problem. So we call this approach patch-based auditing. Of course, the problem of patch-based auditing system is, of course, the performance overhead. In particular, re-executing is very costly for BG server. It means auditing entire requests require re-execution of all requests again, and also auditing 1 month worth of execution require another month solely for replay. Of course, we developed lots of different techniques to overcome those challenges. We call partial re-execution technique. With control flow filtering, instead of re-executing all the history, why not replaying some of the action that actually affected by possibly affected execution with function level auditing. Instead of comparing entire history together, we now compare the function level execution. And lastly, with memoized re-execution, we can avoid the duplicated computation while re-execution. I'm not talk about this more in detail today, but I hope to have the chance to talk about them later. Putting all together, we now have a genuine way to make our system secure. Given a security patch, not only we can prevent the attack in the future by using security patch, we can now go back and change our history so that we can fix the vulnerability. For example, if we get a security patch from the secure shell server from the upstream, at that point we can quickly pinpoint the entry point of the attack by using patch-based auditing system. So that instead of spending time for manual analysis, we can quickly pinpoint the original entry point of the attack. After you identify the entry point of attack, we can selectively roll back and re-execute so that we can preserve the changes that we made after that. Lastly, because we provide precise dependency tracking in our system, we can now provide very strong guarantee about our recovery. Our contribution a little bit high level is that whenever new patches are released, we can not only prevent the future attack, which is the original intention of the attack, we can now detect and repair the past attacks for free. And this is a summary of our approach in implementing this idea as a real system. First of all, since existing systems are not specifically designed for history in mind, we first define our new data abstraction called action history graph. And also, in order to make this approach more practical, we introduced 2 new re-execution techniques. Secondly, detecting attack by using history is quite difficult, so that we introduced patch-based auditing system, so that we can automatically pinpoint the original entry point of the attack. Lastly, in some cases, history cannot be changed. So in fact, we couldn't solve this problem entirely, but in some cases, we can provide some compensating actions so that we can help users to understand their repair state. If you like this line of work, we recently published our work, so please check this paper. So in order to evaluate our work, we asked 4 different questions. First, how much better our automatic intrusion recovery than manual repair, and how much runtime overhead does our system impose, and what kind of attack can be detected by patch-based auditing system, and how fast is our re-execution technique. And this is experimental setup for Retro, which is an automatic recovery system in operating system. We use pretty much a standard workstation environment. We modify Linux to support Retro, and we tested Retro with 2 real-world attacks that we collected from Honeypot, and we use 8 synthetic attacks. As a result, we could correctly recover from those attacks, including 2 example scenarios that I was talking about today, and also 6 known scenarios that we collected from literature. And we also measured the runtime overhead of Retro. When we measure the Retro's runtime overhead in realistic workload, the workload of last-minute paper submission in Hackcrack conference website, it imposed about 35% CPU overhead, and it imposed about 4 GB per day storage overhead. We also measure the performance overhead even in challenging workload, the workload of Apache server serving small static files, and with the continuous kernel recompile. For those cases, our system imposed 100% CPU overhead, and we impose about 150 gigabyte per day storage overhead. It means that we can store approximately 2 weeks of logs on 2 terabyte of disk, even for worst case workload. If you have your system, if your system have extra core available, you can actually dedicate the core to retro so that you can improve the performance of retro. It means that for a system where recovery is very critical, the retro's overhead can be acceptable by those systems. This is the experimental setup for Poirot, which is a patch-based auditing system for web application. We use pretty much a standard workstation environment for web server, and because we implement Poirot in terms of PHP bytecode, every web application that was written in PHP can simply take advantage of this patch-based auditing system. We test Poirot with real security patches that we collected from Wikipedia and Hackweb, and we test Poirot's runtime overhead under real Wikipedia traces. First of all, Poirot efficiently would pass attack. When we test Poirot with 34 real patches that we collected from Wikipedia, for most of the patches, we could quickly audit the entire execution, like 3.5 hours of execution within seconds. For the rest of the patches that require re-execution of entire request, it took about 10 minutes. It means that Poirot can re-execute 10 to 50 times faster than the original execution, even for worst-case patches that require us to re-execute everything. Also, Poirot detects real attack. Poirot could detect 5 different types of attacks in Wikipedia, and Poirot could detect 4 information leak vulnerability in Hackweb. We also measure the performance overhead of Poirot. When we test Poirot with real Wikipedia traces, it imposes about 15% latency and throughput overhead, and it imposes about 5 kilobyte per request storage overhead. It means that for a system where integrity is really critical, the Poirot's overhead can be acceptable by those systems. Of course, there are a lot of related work. For tracking down attack, there are backtracker and introvert. However, unlike those systems, we not only provide an automatic way of tracking down the attack, and actually we recover from them. Secondly, Taesoo and Polyglot are using taint tracking for recovery. Unlike our system, they are suffering from false positive that ends up recovering all the files in their system. Undo over make store implement the application-specific undo and redo, but in our system, we provide a general way to undo and redo in application by modifying the operating system, particularly for intrusion recovery. I was mainly talking about retro and Poirot. Now I'm going to talk about my future research agenda. Today I was talking about how to use history for automatic intrusion recovery. But in fact, we can use history for everything else. Then we can do a lot of crazy stuff. The interesting question that I like to answer in particular is that how can I make the undoability be part of our daily computing life? As we conveniently use undo and redo in our text editor, can you make the exact same thing happen in our operating system? Then what kind of operating system component and interfaces should be redesigned? Also, in order to make this project more practical and deployable to the real world, we need to develop unusable yet intuitive user interface for the user. And those are the key questions that I like to answer during this project. Secondly, all of my past work rely on the fact that my underlying kernel is secure by default, which is never be true in practice. Then how can you protect our history from adversary? In other words, how can I make our underlying kernel be secure by design so that we can securely keep track of their history and we can keep the recorded history in a secure way? With the advances of program languages, there are a lot of attractive features that develop. Particularly, purely functional property in Haskell, we now have better chance to implement the undo and redo ability in our implementation so that we can make our system more plausible in the real world. So lastly, we now have a nice and clean history of a single computer. Then how can I merge, how can I connect the history of all computers, probably all the computers in your corporation network and university network? Then we might be able to have better understanding of the security based on those concrete history. Thanks to the big data, we now have great tools for processing large amount of data. So we might be able to understand global security, whatever property you can extract out of those concrete history at scale. We believe this is the right moment to implement this idea. In quick summary, today I was talking about how to build secure system by using system-wide history. We believe this is a big step toward undercomputing, and in order to support this claim, we design and implement 4 real-world systems for automatic intrusion recovery and automatic way of detecting past attack. And thank you.
Yeah, questions?
So with retro, is it ever safe to discard old history, or do you just have to save 100 gigs per day?
That is a good question. Actually, it is not safe to discard all the log, because in order to support some missing dependency in the past, you always need the log. But if you're concerned about the storage overhead of the logging that we provide, you can actually transform the fine-grained log to the high-level form. Yes.
So this point about sort of pausing in response to user input because you don't know how to replay it seems really important, because it means as an attacker, I don't target PDF LaTeX, I target your editor, and I mix together my changes with your history, and I like drive up the cost, and you keep a finer grained history, which drives up your overhead. And I'm just wondering what you think there.
I see. Actually, there is one interesting argument about this phenomenon is that if, as an attacker, if you introduce a lot of changes in our system, we actually can immediately detect this behavior. What if you delete the password file? Then actually we immediately detect this behavior in our system. So we don't need all the machinery that I was talking about today. We can just roll back immediately, and the system might be working from that point. The interesting case here is that in terms of attacker, they want to hide themselves and exploit something out of my system, probably resource and running botnet. What they want is like not introduce big changes to your system, but whether they want to hide themselves. So that those are the difficult case that we have to tackle.
Well, I guess that's the case I'm describing, where I stick a little bit of code inside. So I Trojan your editor, and every time you open the keys file, I delete my key, and when you save, I write it back. And slowly over time, see these things around your system rather than all at once. And so then when it is time to replay it, my edits are mixed in with yours.
Yeah. Oh, another interesting interface that we provide is that if application want to provide their own semantic, actually we provide some couple of system calls that application use. So that application embeds their own notion to our system so that they can create nice, clean action to our action history graph, so that they can actually remove those operations that you described, if your editor actually support our system. Yes?
The previous point, but so have you thought about this sort of from the other side? So if I'm an attacker and I'm attacking a system that I know is running like an undo operating system, how do I attack that system? Like how do I change
we believe our kernel is secure by default. We actually rely on the security of like kernel and hardware, so that if I'm the attacker, I probably create the external dependency that I couldn't figure it out. For example, I probably leak my password and log into the password to my computer system. So there is a leaked dependency between them, so I can achieve my stuff.
So if you could design, if you could change the hardware in any way that you wanted to, let's say you could change the memory interface or something, what would you add or remove or change? Oh,
one interesting feature that I want from the hardware is that I'm not sure you probably see the literature from Cornell and UPenn. They provide some dynamic way to keep track of their dependency in the instruction level at the hardware. So if you have these kind of features, you actually reduce down the dependency tracking in your kernel. And also, if your hardware provides some attestation technique, so that we can keep our log in secure way, it would be great to have those kind of hardware.
Thanks.
Yeah, thank you.
Thanks, speaker again.